so we have a different problem here. We don't have a sum, we have an inequality, and we want to show that 3 to the n is greater than 100 times n for n greater than 5. And so, again, plugging in values for n so that you believe that this is true, I find to be very helpful. So when we show condition 1, we're no longer using n equals 1 because of what's given. So we have to say, since n is greater than 5 and n is a natural number, we have to use n equals 6. And so when n is 6, is 3 to the 6 greater than 100 times 6? Well, 3 to the 6 is 729, and we know 100 times 6 is 600. So it is in fact true that 729 is greater than 600. So condition 1 holds. And notice that we don't need to show that the statement is true doesn't always have to be for the first term. It's just for whatever value of n is going to work. For condition 2, we want to suppose the statement holds true for some, and then this is n equals k. And so this is going to mean that that is 3 to the k is greater than 100 times k for k greater than 5. And then what we want to do after this is that, assuming that this is true, we want to show the statement is going to hold true for n equals k plus 1, the next term. So that is, we're trying to show 3 to the k plus 1, so I meant to write this here. So 3 to the k plus 1 is in fact greater than 100 times k plus 1. So that is what we want to show, that the next term is going to be 3 to the k plus 1 is in fact greater than 100 times k plus 1. So to show this, we might as well start with one of the sides. We know that 3 to the k plus 1 can be expressed as 3 times 3 to the k. And the reason why I want to do this is that I know from the induction hypothesis that I want to get to something involving that induction hypothesis, that statement where n equals k is true. And so I'm always manipulating somehow or using the terms to identify the kth term. And so now I can say that 3 to the k plus 1 is equal to 3 times 3 to the k, which is then going to be greater than, because we know 3 to the k is greater than 100k, is going to be 3 times 100k. So the 3's don't just drop, they kind of come along for the ride, and that's because it's just this we know to be is greater than 100k from the induction hypothesis. So the 3's stay there for just like, because it was already there in the first place. And so what we still want to show is that the k plus 1 term is greater than the 100k plus 100 times k plus 1. So what we need to show is that 3 times 100k is 300k. We need to show that this is greater than 100k plus 100. So what is left to show is the 300k, is that greater than 100k plus 100. And this came from the fact that we're still trying to show that this inequality is holding true. And so we got to the point that we know that 3 to the k plus 1 is greater than 300k, but we still need to show that that's greater than 100k plus 100. And so what we're trying to utilize is that as long as we know that this is true, as long as k is greater than 5. And so if I solve for k, I'll get 200k is greater than 100, so making k be greater than 1/2. Well, okay, so anytime k is greater than 1/2, then k is also greater than 5. So what that tells us is, since k is greater than 5, we have shown the next term has been, we have shown the next term, the k plus 1 term. And so the reason is that since 300k is greater than 100k plus 100 for k greater than 1/2, and we have that k has to be greater than 5, well then this is always going to be true for k greater than 5. So the conclusion is, since conditions 1 and 2 are satisfied, the statement is true for all natural numbers by mathematical induction. Alright, I'll see you in the next problem.